Let's take a look at different families of functions. First group we're going to look at is a pretty big group. It's the rational functions. Now, a rational function is defined as anything where you have p of x over q of x, where both of those represent polynomials. And in this case, we're going to allow polynomials to include things like constants. So if q of x was 1, p of x could be any standard polynomial. Whereas if q of x was, let's say, x squared or x plus 5 or something like that, then we'll have some strange behavior that happens with our graph. So let's take a look at some of the possible cases. The first one is a special case where we have the inverse variation function. And in this function, it's y equals 1 over x. It's specifically that, or in this case, any constant, y equals any constant over x. One way to recognize this is that you're going to have two asymptotes. Both of the axes will form your asymptotes here. And you're going to get this kind of funky, swirly behavior where the graph is going to shoot up towards one of the asymptotes, shoot over to the other, shoot down in this way, shoot back to the other asymptote. And that's something you're going to always see with an inverse variation function. Another type of rational function is a quadratic function. Now, quadratics are anything with a x squared term that you have inside. Now, the other terms, such as the x term or the constant, may be 0, but you always have to have an actual x squared term to be a quadratic. As far as other special cases with rational functions that I don't have pictured here, you could have something that looks like a line, except for the fact that at one very special point, or maybe more than one very special point, the line is undefined. That would be considered a hole. So holes come up in some rational function. Other ones, like this one here, where you have it approaching a certain value, both in the x and the y, is going to have the asymptotes. So asymptotes and holes are both ways to recognize rational functions where we have something going on in the denominator. A quadratic has nothing in the denominator but has an x squared term in it. Now, moving into specifically linear functions, first example is a constant. Y equals some number, and that's how it's going to be a flat horizontal line. Another one, a little more interesting, is the direct variation function. This is just a typical line, y equals ax, where a can be any number, anything that's not 0. However, it does always pass through the origin. So if I was writing a function and it looks something like this, I would have to make sure that it did in fact pass through the origin in order to be direct variation. You'll notice that unlike the equation of many lines, there is no y-intercept here. It's just going to be plus 0. That's how you know it's a direct variation. It's a line without a y-intercept. And then finally, last special case of linear functions is going to be y equals x. That's a very specific direct variation where the slope is exactly positive 1. Y equals 1. Y equals x. So, as far as types of linear functions, there's of course the standard line, which is not pictured here. There is a special case of a flat line, a constant function. Special case of the direct variation, where you always pass through the origin with your line. And then the extra special case of the identity function, where not only do you pass through the origin, but your slope is exactly 1. Technically speaking, all these classify as rational functions. Whenever you're classifying these, just make sure that you use the most specific case you can. Down below here we have some that don't fit under the category of rational functions. First one is the greatest integer function, which is also called the step function. It's easy to recognize because the graph looks like steps. So whenever you see this discontinuous step-like graph, you know you're dealing with the greatest integer function. Next one is the absolute value function. Absolute value is always going to form this distinct V shape. Now, sometimes the V will be more gradual, sometimes it'll be steeper, but it will always form that V shape whenever you're dealing with y equals absolute value of some function relating to x, such as y equals 3x plus 1, all in absolute values, or just simply y equals absolute value of x. Finally, we have the square root function. The square root function is best recognized by something that starts going up fairly quickly and then tapers off fairly shortly afterward. You can imagine a parabola, if we go up to our parabola up above, tilted sideways. Whenever you have a parabola tilted sideways and you're only looking at 1/2, that's going to have the same rate of increase as the square root function. So effectively, if you have a graph that looks like a parabola tilted in its side, but cut in half, you're probably looking at a square root function. So let's take a couple examples here and see if we can identify these. Well, this first one sounds a lot like what we just talked about. It kind of looks like it would be a sideways parabola if we continued on. And in fact, that is the square root function. This next one here looks like it's a line. So we would say, oh, it's linear, and look, it passes through the origin. Great, so it's a direct variation if we want to be more specific. However, we've got a problem. We've got this hole here in our line. Now, whenever you have a hole in the line, you can't classify it as a typical linear function. You just have to call it a rational function. It doesn't qualify as the special case of being an inverse variation, so just a standard rational function would do for this one. Next problem, we're looking at Emily, who launched a toy rocket from the ground. The height above the ground level h in feet after t seconds is given by this formula here. Which graph depicts the height of the rocket during flight? Well, we have a -16 t squared graph, and the rest of it is just a polynomial. Whenever you have a t squared term, an x squared term, any variable to the second power, you're usually looking at a quadratic equation. So what we have is we're trying to identify where is our parabola, where is our u-shaped graph, and that's going to be B. So we're going to choose B because it is the parabolic shape. It also makes sense that in time a rocket shoots up really fast, slows down as it reaches its peaks, and then starts falling faster and faster as it gets closer to the ground. So it will be B.